Hier, j'ai joué un groupe.
Le stream marche bien. Juste ça, c'est sur l'ordi, je pense. Oui. Bah oui.
Voilà, tu es en ligne, c'est bon.
Ah, en fait, il faut le mettre sur mon ordi.
Cliquez un coup sur votre.
Est-ce que ça change les slides, Laurent, de ton côté?
Bah, oui, on voit. Là, pour l'instant, je suis toujours sur le. Attends, merde, je regarde pas la bonne fenêtre. Je regardais le YouTube. Oui, oui, bien sûr, ça change les slides. Aucun souci.
Parfait. Eh ben, on est bon. Merci, Laurent. Je pense que
Il te reste voilà, quelques minutes.
on attend les reviewers, les deux qui vont se connecter ici. Et ben, merci.
Bon. En Italie, on dit in bocca al lupo.
Ah oui. Bon, bah, bonjour à tous, merci d'être en avance. Ça commence dans un quart d'heure. N'hésitez pas à faire un tour pour découvrir le jardin des vignes à côté. Si vous voulez lire la thèse avant, il y a 3 exemplaires ici, mais vous les rendez au jury avant que ça commence. Je vais en signe de protestation. Il y a déjà 10 000 phrases. Et alors. Check.
Hello, good morning.
Hello, Nicolas. Do you hear us?
Loud and clear.
Perfect. Do you see the slides?
Yes, I see the slides and I can see the big room.
Okay, so that's perfect. So let's wait for Marie-Cécile and the jury. And
Connect now. Then I'll mute myself, do a bio break, and I'll be back in a couple of minutes.
yeah, sure. Thank you. Ah, peut-être éteindre, je sais pas.
Sinon,
On a le temps pour que j'appelle la salle, parce que je sais pas comment on règle. Non, not yet. Euh, ouais, ouais. Ah. Okay. Okay. I'm on the room. Okay, the room. Okay. Yeah. Yeah. Ouais, ouais, Maybe, Nikos, could you cut your camera because connection is not really good. I have a small delay. It may help.
Okay, I'll turn off my camera.
Thank you. Euh, ouais, ouais. Mm. 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 Hop. Okay. Okay. Good. Oui, c'est bah, de toute façon. Ah. Ici. Ok, super. Laurent, Laurent online, tu es là. Laurent Chiatti est là. Or Nikos, could you confirm the slides are moving well?
Yes, I think they're
Thank you.
going. It's very well. I can hear you very well, and the slides are fine.
Good. No delay. Fine. Marie-Cécile is still not yet here. Ah, here she is. Hello, Marie-Cécile. Do you?
Yes, can you hear me?
Yeah, we can. Do you
Okay.
see the slides?
Yeah.
We're good to go.
So good morning, everybody. It's my pleasure to be president from this PhD defense. So welcome to the public, welcome to the estimated jury, and welcome, of course, to the PhD candidate to defend his public research that he has done. But before we start, I would like to introduce a little bit the jury of the composition of the jury here for this PhD student. First of all, we have Nicolas Antonio, who is online. You will see him maybe in a small screen there, and Marie-Cécile Alvarez-Hero. You'll always see her online at her office. Then we have Stéphane Busset, Hakin Ardun, Robin Girard, Paginatus Andrayasis, that's a little bit difficult in my pronunciation, Olivier Depois, Hélène Clément, et finalement Benoît Saunier. Before we start to the public defense, I would like to ask you to decline your phone, or at least the sound of the phone, in order to not disturb the candidate. So, and also before we start with the real presentation of the candidate, I would like to invite Olivier to give a 5-second the setting of what is the research in this group, in order to see what the relation to the PhD research.
Thank you, Mr. President. Well, when we started this work 3 years ago,
As a TSO, we were really interested to know what are the benefits of DC solutions, what they could provide for us, for grid connection, for different types of resources. There is quite a lot of literature on the DC capabilities on the technical side, but we realized that we had almost nothing regarding the technical, the cost benefits analysis. So this is the main driver for us to launch this work, especially also with SNCF on the industrial side. So thank you, Mr. President, and I think.
So thank you very much. And Laurent, the floor is yours.
Thank you, Mr. President. Just let me start my small. Okay, and thank you everyone for attending my PhD defense, which is called Decision-Making Methods for Connecting Medium, I tell here, Voltage Direct Current Solution to the Transmission Network. My thesis is supervised by Robin, director, Panayotis, Olivier, and Hélène, co-supervisors from InParis PSL and RTE. So before going into the topic, I would like to introduce the fact that DC is making a comeback nowadays in transmission network. So this is mostly driven by what we call HVDC, which is high voltage direct current. So it drives the transportation of electricity through three applications, long distances. So the record is in China with 8 gigawatts and more than 2,000 kilometers. It also is useful to couple non-synchronous grids, such as the link between France and United Kingdom there. And finally, it's widely used for submarine cables to connect offshore wind plants. So in this graph, you have, it's an interesting graph from the IEA showing the growth of HVDC link, both in terms of distance and capacity in gigawatts. It's mostly driven by China, but the rest of the world is following, and HVDC has become an industrial solution nowadays. In Europe, you see the transmission network there. DC links are in pink. You can see it's mostly in North Sea and in sea most of the time, which show also the fact that even in Europe, it's a fact. A second trend, which is interesting, is the decrease of AC-DC conversion cost. This is quite an old graph from Fraunhofer. 10 years ago, they managed to evaluate the decrease of cost of AC-DC conversion with the application of inverter for PV applications, so the device which is converting the direct current of PV to AC. And they saw that with the growing capacity of this equipment, the cost was decreasing for small-scale PV inverters and also large-scale. And we made the exercise to continue this graph, and now we are here for large-scale inverters. So you can see the trend was accurate, and as the volume continued to grow, the price went down as well for large-scale PV inverter. A third trend is the energy transition. Energy transition means more photovoltaic, more batteries, more electric vehicles, more hydrogen, more data center. Is it energy transition? I don't know. And nowadays, you have vast capacities or consumption in France. But in 10 years, from the bilan prévisionnel from RTE, which is a French TSO, you can see a large growth for all these devices in the network. So a multiplication by 2 for electrolysis, it's even like exponential growth. And so all these DC consumers and DC producers bring new opportunities for DC networks, because we have lots of DC users in the future grids. And it's already the case, by the way. So when we talk about DC, let me introduce you differences between voltages, just by showing you a few applications of different level of DC. So on the low voltage side, LVDC, you have what you have in your computer, converter unit for a computer, converting AC from the grid to DC to a computer. At the medium voltage side, 1.5 kilovolts, we have DC trains. Some trains, electrified trains, are consume DC current. And in the medium voltage side, you have the Angle DC project, which is a flagship for medium voltage. It connects an island, isolated island in United Kingdom, to the mainland continent using here a DC link at plus minus 27 kilovolts. So this is a non-standard application, but still it was an industrial realization of such a project. And on the high voltage side, you have HVDC converter station. You can see it's quite huge installation. And at the very high voltage, ultra high voltage, in China, you have this large installation. On the AC side, I won't go to the application of AC, but I can say that in France, we have a distinction between distribution below 50 kilovolts and transmission above. For distribution, you have many stakeholders in France, and transmission, the monopolistic stakeholder is RTE. And this thesis will focus on MVDC. So I define MVDC in my thesis as 1.5 to 100 kilovolt DC. And also my thesis will mostly concern transmission systems. As you can see, because for MVDC, because it's below and above 50 kilovolts, it's unclear whether it's transmission on this side or distribution on this side. So I will develop the application for transmission and RT in the French case. And this thesis also focused mostly on techno-economic questions. And we want to know the economic viability of MVDC. So it's a solution, it's technically viable, but is it interesting economically? This brings several questions and challenges. So, well, MVDC, it's an application, it's a technology, there are a lot of use cases. So maybe it's interesting in some use cases, maybe in some other it's not. So we have to answer this broad question of MVDC interest in general, we have to distinguish the different use cases. MVDC is not the same as AC, of course. It brings also new possibilities, new services. So we have, when we compare MVDC to standard AC solution, we have to take that into account. I mean, MVDC can bring something new. And finally, MVDC is a non-standard technology, which means nowadays, as I said, angle DC is new, and MVDC is not standard as are transformers or AC lines. And this brings a difficulty concern regarding hypothesis in the models, because now MVDC, yeah, it's like PV like 30 years ago, or maybe 15 years ago, let's say. We think there is a thing, but hypotheses are mostly prospective, so we have to manage that. So, and also another challenge is the fact that its potential remains to be assessed. Even if we found one use case where MVDC is interesting, it's not sure it's the potential for it. So the number of megawatts you have to install in terms of industrial application is enough to support MVDC widespread. So we have, it would be interesting to assess the economic potential of MVDC. So the two research questions which are driving my thesis are the following. So first, we need methods, techno-economic methods, to assess the connection of MVDC solution, as I say, to the transmission network. And the second question, more applied, is the question of the potential, this potential I was talking about, to the transmission of MVDC solution. And my use case will be France, with French hypotheses, French use cases. It may be different for other countries, but for France, it's already complex. When I look into the general literature on MVDC techno-economic methods, I separate two big MVDC techno-economic methods. The first one are very general. It's cost-benefit analysis. You compute the cost, you compute the benefits, you compare them, you say, okay, benefits are more important than cost, then it's a good solution. So there are some papers, some reports on this, and you can see on MVDC, the literature, as I said, it's a new technology. The literature is not very spread on economic, but you can see it managed to go from microgrid distribution up to plus minus 60 kilovolts, so within the MVDC range. And I'll talk about this paper a bit later in the chapter. And the second big method we can see in the literature are transmission and distribution expansion planning. So these are techniques and methods dedicated to network reinforcement. It's not applicable to all kind of MVDC solution connection. And here, the literature is very well detailed in distribution. We have this paper citing 4 of the works, this paper from Faraz Debarros, which is very important, I think. And on the HVDC side as well, think some of my jury members are really specialists on that. So just this paper sits 38 works just in the current year. So this is a very well studied with very detailed method, but it's rather HVDC, and you can see there is kind of a gap here for MVDC. I'll go back on that later. And there is a missing literature, which is the literature from the industrial. There's no literature from DSO and TSOs, as MVDC, as I say, is non-standard. And the industrial do publish their components when it becomes standard. But at first, from RT, then in this, there's no clear statement about the economic of MVDC, I would say. And also, there's no literature about MVDC potential in France. So this is a gap in the literature to assess the MVDC availability. So the plan of this presentation will be, so this presentation will be separated in 3 chapters. You can see them here. And we will answer to the 2 research questions with 2 objectives. The second chapter of the thesis is dedicated to MVDC connection of DC resources to transmission AC network. We will present a method to compute the cost of DC resource connection to transmission AC network. And we'll do a cost comparison of point-to-point and shared transmission connection for the objective 2. For the chapter 3, we'll be interesting into the MVDC connection of DC resources to MVDC network, different from here, AC transmission network. We'll also describe the method to connect to MVDC network, and we'll apply this use case for a special MVDC network, which is a railway MVDC network, and we'll find the potential for solar plus battery connection, which is a kind of DC resource. And finally, I will explore MVDC in transmission expansion planning. We will describe shortly a method to optimize network reinforcement with MVDC investment option, and we will apply it to an EEE 118 bus, which is standard network modified network. So for chapter 2, now I'll go into each chapter. Chapter 2, what is the motivation of chapter 2? Basically, you have DC resources, 1 or 2. In my thesis, I'm limiting to 1 or 2 DC resources. You want to connect it to a unique AC network connection point. The question is, what are the connection costs? And deriving from that, should I connect into AC or MVDC? What are the equipment, etc. So when we look into the literature, there is, for instance, this interesting report where it's a team from the South Korean TSO, and they, but inside the IEC report, and they compare the connection of a 60 megawatt client, whether in AC with a high voltage line, whether in DC in medium voltage. They drive the costs, which depends on the distance, and they found, okay, at 40 kilometers per MVDC becomes cheaper than AC. There is what we call cost break-even distance of 40 kilometers in this case. But what they do in this analysis is the fact they only use equipment costs. They don't consider losses, they don't consider reliability, they not optimize the ratings, etc. So it provides a really good information. I mean, it's the first step. But still, we see that all costs are not always considered, and we need a method that considers all these costs. The second problem with this kind of study is the fact, as I mentioned before, hypotheses are uncertain in MVDC. It's a prospective technology, basically. And you can see this paper. So they compare different connection schemes. So it's for networks, but they compare different schemes with a cost of DC-DC converter of 15 euro per kilowatt. And when they compare the 3 options they have, they found that MVDC1 is the cheapest. But this value is maybe optimistic, because nowadays I can disclose confidential information, and it's not an easy information anyway, but the value is more close to 100 to 200 euro per kilowatt, since it's not this value. And if you apply this calculation with 100 euro per kilowatt, you find that MVDC is not the best option. So you have to take care of the different hypotheses. Many hypotheses, many uncertainties. So we need a method that can do a lot of sensitivity analysis, in my opinion, because sensitivity analysis are allowed to explore a wide range of possibilities, such as converter cost. So on the method, I won't describe it in detail, but just taking back my 2 needs. So answering the first need, what we did is a step-by-step method where we compute capex, fixed opex, operational losses, reliability cost, and reactive power provision benefits. There are other costs that could be computed. I'm sure we will discuss that in the question. But it's already a wide range of costs in comparing with the literature. And this includes an optimization of the operational rating, and we mostly use mixed integral linear programs, so MILPs. And about the second need, the fact of using MILP allows us to do really fast computation. So the computation is done in a few minutes for a connection option, so which allow us to do a lot of sensitivity analysis and to explore a wide range of hypotheses. Now, let's go to the specific contribution apart from the method itself. So I will present two contributions. The first one is on reliability cost, which I'll define by the cost of the loss of load or production in case of device unavailability. Let's see this example. Should we install one device of 100 megawatts or two devices of 200 megawatts with a 1% unavailability when you want to connect 100 megawatts? So if you have one device of 100 megawatts, whether it's not in fault, whether it's in fault, the chance of occurrence is 95%, 1%. And the cost, let's compute the cost over the lifetime of the connection if this number of device is in fault, so all the 40 years of the lifetime. So the cost is, it's also computed with the MILP. This is important and this is new. And the cost, of course, if you want to supply 100 megawatts, but you can't during all the lifetime, it's a tremendous cost. And how you compute reliability cost, you sum product this probability with this cost. So, and this is the same reasoning for here, two devices of 100 megawatts. And you can see that having one device of 100 megawatts doesn't seem a good idea because 1% of the time you will be off, and in the end, it's a lot of money you're losing. But if you have two devices, it can be more expensive because you have capex here. But in the end, the reliability cost may be affordable. At least it's not the same order of magnitude of the first one. So in this method, consider this reliability matter, and we found it's quite important for consumers. The second contribution is a rough approximation of reactive power provision. So MVDC is often quoted as a really good opportunity for reactive power provision. So what I do in the method is estimating that some of the devices can provide reactive power provision, such as in this connection, this converter can provide reactive power provision to the AC network. And what I say is that, okay, 30% of this rating, so it's an hypothesis, but it's model driven by industrial data, can provide its rating in megawatt, in megawatt, as reactive power. So what I do is I say, okay, reactive power provision benefit in maximum, it's a conservative approximation. At maximum, the benefit is a capex and fixed opex of a STATCOM of 30% of its converter rating in megawatt. So I consider reactive power provision being quite optimistic on the value it has by replacing STATCOMs. And so the numerical application I did, as I mentioned, I did a lot of sensitivity analysis and a lot of use cases. So all the use cases I explore are these ones. Point-to-point transmission of one DC resource for constant consumer, electrolysis DC, PV, arbitrage battery. So there's explore a wide range of DC resources and share connection of two DC resources where you connect two DC resources with a shared connection. So in AC, it looks like that. In DC, in MVDC, it looks like that with a shared transformation of AC to DC power there. I also explored overhead lines and underground cables with different voltage levels. So for MVDC, I'll explore plus minus 20, plus minus 35, plus minus 50 in DC. And in AC, we have AC standard. So in France, I can't install the AC voltage I want. I'm obliged by the law. So on AC, I just have 63 kilovolts, and this will have an importance. I tested several couples of connection length times DC resource rating, so you can think that, okay, but it depends, do you want to connect 10 kilometers, 10 megawatts, etc. In France, there is regulation, and the connection to 63 kilovolts depends on the line length and connection rating. So I explored the dots, black dots here, I'm respecting the French regulation thresholds. So that's why I explore low rating, high length, and high rating, low length. And finally, as we mentioned, DC-DC and AC-DC converter costs are quite a prospective hypothesis. So I did test a present value. So these are the present value I found, and more details are in the manuscript, and prospective values, which are, in my mind, quite optimistic values, but maybe in some time, the industry will be able to deliver these products with this cost. So the kind of results I have. So this is what kind of results. So I explore point-to-point connection. I connect an electrolysis plant, and I have different ratings and length. And you can here see the display of MVDC cost minus AC cost. So there are numbers in million euros. But roughly, if you just want a sense of what is happening here, in red, you should do AC. In green, you should do MVDC. So what can be inferred from this graph? So you can see the longer the line length, the more the MVDC connection is preferred, the more you have green. And the higher the rating, the more the AC connection is preferred. This is very similar to HVDC point-to-point analysis. So this is an example of a paper where you can compute the transmission depending on the transmission, the cost. If you have low distance, AC is preferred, high distance, DC is preferred. And also, if you have high rating, the gap between DC converter station and AC station increases. So the cost break-even distance becomes higher. Other results from all the sensitivity analysis use cases divided in point-to-point and shell connection results. So first, MVDC should be envisaged rather for underground cables, because underground cables are more expensive on overall, and it saves more cost. Second, MVDC is less interesting in countries with many AC voltage levels. As I said, in the use case, I'm obliged to install 63 kilovolt AC. But if you have other options of AC voltage, then the gap between MVDC and AC becomes thinner. And MVDC solves AC voltage gaps, but if you have more options, maybe it has to be investigated. Reliability consideration may change the preference between MVDC and AC for consumers. I find that for producers, taking reliability into account is less interesting, because loss of a producer is less money than losing a consumer from standard industrial hypothesis. That's why it's rather for consumer reliability. And finally, reactive power compensation. On point-to-point, on what I found, it doesn't drive the interest for MVDC. It's a nice have to MVDC, but still, it's not the main factor triggering MVDC interest. And finally, for share correction, just one result. Intuitively, we could say, okay, if you share the connection, you can share the AC-DC connection. So this converter will be lower rating, maybe it will save money. Yeah, that's true. But here you have DC-DC converters, which are expensive. So even if you share a connection with MVDC, the fact that DC-DC conversion is obliged and DC-DC converters are expensive makes the fact that share connection of two DC resources don't justify the interest for MVDC, at least for a PV panel, which is intermittent. The contribution of chapter 2. Concerning objective 1, we propose a generic method to compute connection cost, including rating optimization, capex, fixed opex, reliability using MILP, and losses and reactive power compensation. And the method, thanks to the MILP formulation, is really fast, allowing for many sensitivity analysis. We applied that to numerous use cases adapted to France, and we found, I would say, qualitative results and reasons to choose MVDC drivers for MVDC choice. This chapter led to 2 publications in 2 conferences in AC/DC Global 2025 and EHDT Europe 2024. So now going to chapter 3. So now the motivation is you have a DC resource, just one, and you wonder, should I connect it to the AC network or to the MVDC network? And again, what are the connection costs? What is the cheapest option? So the use case I chose is Railway MVDC, which I will call RMVDC, and hybrid power plants. While Railway, because when you talk about large MVDC networks, you can think of collection networks, you can think of data center, maybe MVDC network, which is a bit trendy, but the largest MVDC networks are RMVDC. You can see the electrified networks in Europe here. in blue and yellow, you have RMVDC network. So the south of France is RMVDC at 1.5 kilovolts. And why HPP? Well, it's because it has a high potential in France. We have a lot of solar panels that can be installed in France. And I added the battery because I feel like, and I think SNCF will agree, battery is needed. If you could just connect a photovoltaic plant, the production has to match the train demand. If you don't have flexibility for that, it becomes a bit difficult. So that's why there is battery here. When you look into the literature, RMVDC smart grid is a thing. It's a trend. There are papers talking about that. There are searchers looking into. You have your train. You connect here hybrid power plant. This is an hybrid power plant with battery and the solar. You can connect also wind power, EV charging station. So there are people investigating that. But I didn't find a lot of literature, or if any, that is talking about connection cost. Because okay, you can plug a HPP if you want, but maybe it's better to just plug it to the classic AC network, which is done for that. Whereas RMVDC are not designed to host resources at the first place. So we need a method that compares RMVDC and AC network costs. A second trend is why my thesis was funded, by the way, thanks to the Cordi project, which is a collaboration between SNCF, RT, and other stakeholders. And this collaboration investigates the upgrade of voltage between 1.5 kilovolts in France to 9 kilovolts. So this is useful to delete substation. You just need 2 substations in this example instead of 6 there. So this is a thesis from Andrea Verdicio, really interesting and one of the bases of my work. And we may wonder, okay, you want to increase the voltage, it's cool for substations and the losses, the catenary material, etc. But maybe also there are other opportunities of increasing this voltage. Maybe you can connect more DC resources thanks to this increase. So we need an assessment of the impact of higher RMVDC voltage. And so far as I know, this was not done yet. And it's something I did in my thesis. Taking back our 2 needs. So about the method that compares RMVDC and AC connection costs. So we computed, the method calculates CapEx, fixed OpEx, operational HPP, RMVDC loss cost. There's no reliability there, but remember that I told reliability is for consumers. So. And this embeds the operational optimization of the HPP considering RMVDC constraints through a mill. I will go back on that. And higher voltage, how do you do it? Well, again, this is a mill. This is a fast method. So this allows for many sensitivity analysis. So I tested different voltage levels, including the prospective one of the Raccordé project. About the contribution, I want to point out 2 contributions, again, of this chapter. The first one is the modeling of the power flowing through the HPP or the train. So basically, the modeling I made is this one. I have catenary with different voltages. I have rail with other voltages. You have a train or an HPP which is connected between the catenary and the rail. You have a current flowing through it. And in physics, the power in megawatts that can be inferred from these values is the multiplication of the current times the difference of voltage. But if you want to optimize the operation of the HPP, you have a battery, you want to optimize how it works, but then it's not very practical because the current is an optimization variable, the voltage is as well. So this is a quadratic constraint if you impose the power there. And quadratic constraints are more time consuming. So they are difficult to manage. And we chose to propose a linear approximation, just replacing this difference with the substation voltage source there. So here it's a linear constraint because now the current is just proportional to the power. So we did an afterwards analysis of this approximation, and we find that the mean absolute percentage error from this approximation ranges up to 2%. And also, I won't go into the details, but doing this approximation violates the voltage constraint of the catenary, but I found that this violation is magnitude of maximum 0.1% with the approximation for, on my opinion, it's an acceptable approximation, at least for the use cases I consider. The second contribution is rather explanatory contribution, I found I think a nice way of showing whether you should connect to the RMVDC or AC network. So imagine you have an HPP, you have two distances to the RMVDC network and to the neighboring AC network. And the solution, the best option, depends on these two distances. If you are close to the RMVDC network, you wonder, okay, maybe it's cheaper to connect to it, and it's the same for AC network. So I displayed that into this graph. Oh, can someone? Thank you, Ben. So the graph, yeah. So this displays the distance to the AC network and the distance to RMVDC network. I drew a line, and if you are below the line, it means you are close to the AC network, far from the DC network. You should connect to the AC network. And here, if I above, I'm close to the RMVDC network, far from the AC network, I should connect to the RMVDC network. And the line, of course, changes depending on all the parameters of the study. And this is nice because if you have a project and you know, okay, I'm 8 kilometers from the AC network and 2 kilometers from the RMVDC one, I'm here, I'm above the line, I should connect to the RMVDC network. Now, we're looking into potential. So what I did is list the potential of PV. So don't be afraid, I didn't destroy forest or landfills. This is only like not usable land, not stones. This is a database from IGN, Cerema. And and in blue, you can see the Railway MVDC network. I filtered up to 10 kilometers to not explore solutions which are not economically viable even intuitively. What I did is I zoomed into potential, and I cut this area into small squares. Each square is one site, 0.25 megawatt HPP. And they applied a clusterization algorithm by clustering the squares and finding that each cluster of square is one site for 1.5 megawatt HPP or 12 megawatt HPP. This leads to this potential nationwide. So it's up to 23 gigawatts for small scale plants and 13 gigawatts for large plants. So the potential decreases with the rating because, of course, when you have 12 megawatts, there are some areas you can't install. So for instance, you see this small area there. It disappears at the 20 megawatt because it can't host 20 megawatt solar panel. But of course, not all of them are relevant for MVDC connection. I don't say that you can connect 10 gigawatt to the MVDC network. So what we did, we apply the method on each site to find if it should be connected to the AC or the RMVDC network. So it's quite simple. It's just for each site, you have the distances to RMVDC and AC network. You look if you are above or below, and you count the number of sites above the line. And this lead, and a second filter is applied to consider several connections between the same substation, because if one site and just one and next to it can be connected to the RMVDC network, it doesn't mean that the two sites can be connected at the same time to the RMVDC network, because each other are consuming the train power. So we applied the filter to take into account for that. Finally, for the current RMVDC network, for small scale HPP, we find a potential which is rather low, 16 megawatt, not much in comparison with the total capacity. And I also did a map to see where the sites are, so mostly in the south. But if you take prospective RMVDC networks at 9 kilovolts, then the potential drastically increases up to 464 megawatts. So the conclusion is indeed that prospective network presents way more potential than current RMVDC networks. So we did a lot of sensitivity analysis, and this drives over results such as bidirectional transfer station favor RMVDC connection, because if you are bidirectional, you can export the PV production to the AC network. The HPP location matters. If you're close by to a substation, it's not the same thing as if you're in the middle, in terms of RMVDC loss in particular. We considered save the AC network cost in the sensitivity analysis. It favors RMVDC solution, but there are practical ways of doing that which didn't allow us to consider it in the base case. And finally, we tested for wind. And we find, okay, maybe wind, but please be bidirectional in the substation, because if you are at night and you have wind, you don't have train. If you are unidirectional, you can't just, you lose the energy. Finally, the contribution. So we propose a detailed method. Again, HPP operation optimization using MILP, and RMVDC connection loss is taken into account. The method is fast. That allowed for a large national wide potential of HPP connection in France, with a mapping of the interesting seats, and we drove from the sensitivity analysis the intuition of why you should connect to the RMVDC network. This led to a publication in a EGE-PAS journal in 2026 in the beginning of the year. So now for the last chapter before the conclusion. So now it's a different problem. We want to investigate reinforcement network. Reinforcement network, what it is, basically you have an AC network existing. Well, it can also include DC lines, by the way. And you wonder, should you expand it with AC candidates or MVDC candidates? Which candidate should you choose? So the literature on that is really, really important. I mentioned that before. Here is a paper from Faria de Barros. Here's another paper from Conero. But as I maybe introduced, this paper on distribution are rather below 20 kilovolt AC and consider low voltage MVDC, let's say. Or this paper consider HVDC. So there's not many use case for what we could call high voltage MVDC. And I think it's worth to explore this middle area between transmission and distribution. And also, a big notion I didn't introduce is AC counterfactual. In the studies where they look into MVDC, which can control the flow, so it's called soft open point, you will use MVDC to connect different AC substations there. This allows you to control the flows, and then it allows you to manage congestions. But in this study in particular, they only think of AC in terms of reinforcement or new lines. So they say, okay, MVDC is better because you don't have to invest in new lines, new substations, etc. But come on, you have in AC solutions to control the flows. So flexible AC transmission systems is a generic term. And sometimes MVDC study lack the correct, I think, AC counterfactual. So I have to investigate that. So what we did is a DC load flow approximation coupled with an investment problem, resulting again in a MILP. And this time, DC load flow approximation is not valuable for all demand. So this MILP is valuable for large conductors, in my opinion. And we derived that. We added also a linear approximation of SSSCs, with which is a kind of fax I was mentioning. When we look into this approximation, so this is a DC load flow approximation. You have a flow in AC, which is kind of approximated to be linear, depending on the voltage angles. And if you want to model SSSC in a linear way, you can plug to this term a new term here using an optimization variable, and you have a linear term here, and you manage to introduce a controllability of the flow, because now it not depends only on the bus voltages, but also on the control. And SSSC can't be used all the way, all the currents and all the voltage, so we introduce big M constraints to take into account the fact that SSSC are not doing all the, they have a feasibility domain. Results. So we tested that on a 180 modified bus. We did 3 scenarios. One only with AC candidates. Okay, you install AC candidates. The cost is this one. One with DC candidates. Now you see, okay, you decrease the cost, and you have AC lines at some points because AC may be a good option, but you can see that, for instance, there, instead of all these AC lines, you have just one DC line which can control the flows, which is indeed a good capability, and it saves you a lot of money because you can control the flow with this line. But if you add SSSC candidates, now MVDC is not appearing that much. So SSSC is the dot one. And you still have MVDC because at some point MVDC can be useful to increase the capacity there. So that's why there is small MVDC line, which is cheaper than an AC line. but still for the controllability, SSSC is cheaper. And again, the cost decreases for SSSC. So we found, at least within my range of large conductors, with my DC approximation, we found that SSSC is a relevant counterfactual. And of these chapters are this one. So we proposed a MILP embedding operational and investment cost to optimize investment in transmission expansion planning, including best candidates. And about the objective 2, I did a French potential for that, but at least I can say, okay, SSSC is a relevant counterfactual to MVDC in expansion planning. And if you do MVDC expansion planning, consider SSSC because, in my opinion, it's quite a relevant device. And sometimes in the literature, it may be overlooked. So now we are going to the conclusion of my presentation. And I start with key takeaways. So first on MVDC techno-economic modeling. I find that MIL formulation allows for scalable and accurate cost modeling. So this is quite, I think this will be discussed, because MILP, of course, is a relaxation of more complex methods. And it's still an approximation, but still in the studies I made, at first I wanted to do really big optimization problems with taking many things into account, and it led to high time of computation, very complex formulations. And I preferred in the end, and some theses do that and they do it very well, like the one of Etor. But I prefer to explore, as I wanted to focus on potential, I prefer to explore a wide range of costs. And I kind of was, let's say, I think it was more relevant, to use MIL formulation. And in the end, I think that the costs I'm modeling are accurate because I prefer to model a cost with a MIL that's not modeling it at all with more complex solution. Okay, now another thing, existing MVDC network must be modeled explicitly if assessed. So it may be intuitive to connect DC resources to MVDC networks because you say, okay, everything is DC, it's logical. But MVDC networks are not exactly the same as AC network. And this is particularly the case for RMVDC because RMVDC have operational constraints, they have voltage limits, they have losses, their demand is different, etc. So you need to explicitly model them. For AC networks, you have proxies. You can use proxies with using the tariffs, etc. There is a literature on that in industrial practices as well. But for MVDC, it's not the case because it's new. No, you need to model them explicitly, and it's what I did in the thesis. And finally, in MVDC techno-economic studies and in all studies in general, hypotheses are really important. And in MVDC, I just want to recall, I said it in the introduction, but we need to insist on that converter costs are key. Because it's the key element, I would say, the backbone of MVDC economic viability in the future. AC counterfactual, I think they should be considered from the start of the modeling because sometimes when you assess a technology, you go into a modeling and in the end, you can't reach the the objective you set yourself because you are stuck into your modeling options. And you can't bring counterfactual. But if you think from the start of the counterfactual, you may integrate it into the formulation, as I did in chapter 4 for SSSC. On MVDC solution, so this is more like an applied key takeaways for friends. So MVDC can solve AC voltage gap at long distances. So it's the case in South Korea, if you recall the paper I was mentioning. They have only 20 kilovolts AC, and then they have 150 kilovolts. So there is a voltage gap, and MVDC can come into this voltage gap. But you have to consider also AC, which can also be in this voltage gap in AC. Neighboring MVDC network, and especially RMVDC network, are opportunity for self-consumption using DC producers. So as I said, RMVDC can be connected to HPPs. And MVDC capability to control the flow may not be enough, since facts also profile this feature. So I tested controllability of MVDC, but okay, AC can do it as well. It's specific devices, but we have to consider that. On the perspective of my work, there are a lot of them. First big topic is to improve the developed methods. So we think obviously of AC OPF to the transmission expansion planning because my model is limited to large conductor sections, I would say, or to the DC approximation at least. If we want to expand it to distribution, explicit distribution, we need, I think, AC OPF. So that's the main improvement I see in the method. And we can improve the application of the method by geographically do the potential of prospective DC resource in France. Like I could try to locate the H2 electrolysis plant in France, see the distance to the AC network, and try to test if they should be connected in MVDC or AC. I think this is a good one also to test the HPP RMVDC model on a demonstrator for the timing in spirit creation. So if a demonstrator could assess that, we could be sure that the model used is adequate with physical constraints. We could apply the DC expansion formulation on a real network with more representative OS. We could create also new methods, especially on standardization cost, on non-economic decision-making indicators. And finally, I would like to conclude with this picture. I'm like closing the loop because I think this picture was shown by me by Olivier the first day of my thesis. And my conclusion of that is that there are still work to do. The question is not done. And I thank you very much for your attention and thank you for your questions.
So, Laurent, thank you very much for your very nice and in-depth analysis presentations of your PhD work. It was, in my opinion, very good work. Thank you for your input. So I invite as first Professor Marie-Cécile Alvarez pour ask the first questions about your work. Marie-Cécile, the floor is yours.
Yes. Thank you, Jan. Can you hear me well?
It's loud and clear.
Okay. Okay, so thank you a lot, Laurent, for your presentation. That was really nice to hear, as well as your report. So I really appreciate your report, and especially what I pointed out already is your contribution related to the railway system. That to me, it's really original, like to my knowledge, to what I know. I've never seen such study and such a kind of study. Yeah.
Sorry to interrupt. If you want to plug your camera,
oh yeah,
the room.
Yeah. I forgot. Yeah. Okay.
No.
Is it better?
Yeah, we see you.
Okay. And so what I was saying. So yeah, and so it was a very good work. And what's nice is the link you made with the existing literature. I think you really you have analyzed very well what's existing and what's missing. And also I appreciate a lot that you are, let's say, really realistic on what are your contribution and what's remaining. So I think it's your work will really help the community working on this topic of DC. Before some questions, what I appreciate also in your presentation is that I saw that you have addressed some points I mentioned in my report. So it was nice, since we can move on. I won't have time to ask, of course, all the questions. So I will focus on the main ones. So I have some questions, let's say, really specific on the model or on some results, and some questions, let's say, a little bit broader to take some perspective and to have your feedback on some kind of big topic. We will speak later, especially on stability thing. So, okay, let's go. First of all, I have a couple of quick questions about the model you use. And so as you know, I have a little bit experience on this topic and on what's also complex. And one of my questions are about some of the hypotheses and the modeling. Let's start with the losses. For converters, so we know there are some literature that try to make a kind of abacus of the power losses of converters depending on their operating points and so on their efficiency. And it's not linear at all. So the hypothesis of linearity is really good if your converter is working at the nominal power. So you have decided, if I'm not wrong, to linearize this power losses. So can you comment a little bit? So did you check after all, maybe with some simulation, that this hypothesis is not too strong on your scenarios? What is it possible to maybe to improve this model in your MILP? So can you comment a little bit on that?
Okay, do you hear me? Yeah.
Yeah.
President Shai, I'll answer directly, or yeah. Okay. Okay. Thank you for this really interesting question, because indeed I linearize losses, and I have a few. So the problem with my thesis, I have to make you 3 answers, because there is 1 answer for each chapter. So for chapter 2, I have a backup slide on that.
Yeah.
Okay, let's wait. Okay. For chapter 2, as you mentioned, losses depend on the load factor, but it's true that when I look into the results, so it's a post-computational validation. When I look into the results, I see that losses differences are there in gray. So you can see it's very small, except for, indeed, electrolysis plant. But electrolysis plant is a constant consumer. So as you mentioned, for this one, the costs are indeed linear. So I think for the use case I took for chapter 2, let's say losses are not so important for the stakeholders which are not constant consumption. And they are important for the constant consumer, but for this one, the hypothesis is adequate. So this is for chapter 2. And now going into the how could I improve that? I could do it indeed. I think I would. I think the best option will be to include it into the MILP, different. I think it would remain linear to have different cuts on depending on the load factor. So it would remain linear, but what I'm afraid of is that I would need more binaries, so it would increase the computational time for results which, on my opinion, wouldn't be so different for the use cases here. But it's doable. Another approach, which I think would soon more realistic, is to do it post-computationally. Because I do a post-computation of losses, I could embed in this post-computation these nonlinear things. But then the caution I would take is that it brings also more hypothesis, because you need now to have the hypothesis on the shape of your efficiency of converter, which may be a bit difficult. And finally, on chapter 2, there is an issue I would have to tackle, which is the management of the different devices. So it's there. Let's go back to a slide in the beginning. Yeah, so it's the fact of dividing the devices into several devices. So you have one device of 100 megawatt, 2 devices of 100 megawatt, and in the solution I computed, it's more complex. It's like 6 devices of 25 megawatt. It can be well divided. And if you want to compute the losses, you have to decide which device takes which load. Do you optimize the load repartition between the devices in terms of losses? Do you apply all the loads to one device? There are questions of also lifetime. So it's a difficult question in chapter 2 to see the distribution between the different devices to optimize the losses. So I think it's a really interesting research question when we look to you want to investigate on losses, and but it's not trivial in this chapter.
Okay, thank you for the answer.
Do you want me to answer the other chapters, or do you want to?
No. The question was specific on this model, but
okay.
It's okay. We not to spend too much time just on losses. As if you can go back on the previous slides, you show with the graph in your annex, okay. The just the one with all the costs, because it's. I will jump to the question related to reliability. So maybe it's a misunderstanding on my side, but what I wanted to...
This one, maybe?
No, it was with the graph with the cost. The one you used to speak about power losses. You have all the costs.
Yeah.
Just before. Yeah, this one. So, the fact is that I was wondering, because if we take a look to this graph, and so reliability costs are, let's say, negligible, if I may say, especially even compared to losses. And so the question is really simple, is that why? Because it seems not to have an impact. So why, considering the reliability in this study, because you mentioned that if we neglect it, that will impact the capex. So I'm a little bit confused, because with this figure, the first thing is that, okay, so maybe, as you said, power losses I neglect or linearize. Why not reliability? I can neglect it. So maybe my model will be faster and without big difference. You understand my concern?
Exactly, yes. And thank you for addressing that. Indeed, I acknowledge it's a limitation of the manuscript, but it's rather that I didn't convey the right message here and the right graph. I decided to present the graph of the manuscript so that we can see. The fact is that reliability intervenes in reliability cost, as you pointed out, and you're right to say here, well, it's negligible, it's a yellow bar, but it also intervenes in capex and opex difference, because when I compute reliability costs, I do choose in the end, when we think of our two options, I choose the option with the least reliability cost plus the least capex. So I do a kind of manual optimization by minimizing the sum of reliability cost plus capex. And it's true that it doesn't appear in this graph, but indeed, I try to fix that for the final version of the manuscript.
Yeah.
I can differentiate the capex plus fixed opex due to reliability and the one which is not due to reliability. And just to mention, just to mention, here I have a slide. Yeah, without reliability, so these are the final results. And you can see here the difference may be important, like here 11 million euro. So as I said, reliability mostly matters for electrolysis plant here. And here you can see the cost break-even distance, the frontier between AC and DC moves without reliability. But indeed, it's displayed on the capex.
Okay, that's more clear. Okay, that explains. Okay. And so just to let's say the last question on the model. So yeah, basically chapter 2. Yeah, I was a bit surprised. So so you define OPEX in a, let's say, non-usual way. So you express them in percentage of CapEx, so like fixed values. And so I was wondering, so how exactly did you compute and define this? So maybe because I have not the answer, I was wondering, is it because I have noticed that you assume that you don't have any scenarios of load increase? So is it in that sense that you can you compute an equivalent OPEX and you express it in percentage of CapEx, and then you say that it's constant all the year. So can you just explain me a little bit how you define this OPEX as a percentage of CapEx?
Okay, so fixed OPEX are for me, it's fixed OPEX. The hypothesis is not totally OPEX, like it doesn't embed losses, for instance. It's rather the maintenance, the fact you have some cost of gardening, the installation, some stuff like that. So on my side, from RTE perspective, I would say this percentage of CapEx hypothesis is quite standard in the industry. Indeed, and also in the papers I read, I make a big database, and I won't display there, but I would say it was maybe 60% of the data was in percentage of CapEx and 40% in absolute value, depending on the distance or stuff like that. So that's why I took this hypothesis. For me, it's like a reasonable assumption because it comes from industrial standard. And indeed, what we could do to assess this hypothesis is to do sensitivity analysis if we would like to see the impact of the OPEX. And we could also, to improve the modeling in this perspective, I think dissect this fixed OPEX hypothesis, like trying to separate the fixed OPEX between maintenance, between changing the oil, for instance, between gardening. But I think it would go to really technical details on how you manage an installation and such things like that. So it may be interesting, but it's a lot of work. And I'm not sure that fixed OPEX hypothesis is the most important one. And maybe could you develop on the fact you are mentioning of increase of loads, because
because I have to check, but I thought that maybe it's because you express OPEX in percent of CapEx for each kind of OPEX, because what you are saying right now is that the fixed OPEX is only for devices, but not for power losses and reliability. So maybe this, because it was related to that. I thought that, but I have to check again, that this hypothesis of fixed OPEX was also for losses. And of course, if load increase per year, your losses increase per year. So you cannot say the OPEX is fixed.
Exactly.
That's why, okay.
Sorry, so indeed, fixed OPEX is not OPEX, and maybe the word is not adequate because it creates confusions. I agree. But it's fixed for non-losses, non-load-related OPEX, let's say.
Okay, so I have to manage my time. Now let's go to the railway model or use case, let's say. So I will first ask, let's say, a general question, like, okay, to my point of view, to my understanding, your analysis is, let's say, really, you are from the point of view of the system operator, let's say a TSO, a DSO. And I was wondering, okay, if now you are in the railway system operator, okay, so what you propose, so the fact of connecting HPP in several points of the railway system, on this point of view, what are the benefits? In a more general way, do this has an impact on the protections of the railway system, for example, on the operational management of a system? So I guess, I'm not a specialist on railway, but I guess that maybe standards for railway or expectation are maybe different from a power system. I don't know, maybe just an example, maybe they are more strict on interruption, like kind of SID, rather than the transmission system, let's say. So, and I was wondering if you have investigated a bit, like from the railway system point of view, what are the benefits and maybe the drawbacks of connecting HPP to the system?
Okay, Moni, no, no, this is a really interesting question, and I would say that there is large literature on stakeholders' opinion, and indeed, when you install devices in the real world, in the perfect world, you do welfare analysis with collectivity point of view, but in the real world, you have constraints and operators decide. So you're right to address the fact that on my thesis in general, in all the chapters, I consider we choose not to consider stakeholders' point of view. And it's a big field of expansion of my work to address this stakeholders cost. Okay, now for the railway things. So no, I didn't look into SNCF point of view directly. No, what I did is first to answer directly your question, SNCF has a big interest in doing that because of simply cost of energy. The cost of energy paid by SNCF network, and maybe I can follow on that, is quite high. And if you connect HPP to your RMVDC network, it's like self-consumption. It's like PV panel on your rooftop. So you can save money both from the energy, and you don't pay the intermediates, and the AC network cost. So I don't know.
So you suppose that the SNCF would be the owner of HPP in this use case?
Not necessarily, because SNCF can have a purchase agreement with the HPP owner, and they decide the contract. And just wanted to point out in this sensitivity analysis, so look on many sensitivity analysis. So in green, it's when it's better for RMVDC connection. This sensitivity analysis, AC usage network cost. So in the base analysis, I didn't consider that. But if you say, okay, if you connect to HPP, you save the TURP, the tariff of our network, then it becomes really interesting, and you can see the dramatic increase of interesting sites. But indeed, as you mentioned, I will link that to another of your remarks, which are the technical approach of connecting HPP to RMVDC network. So I didn't work on that. I had a validation, I would say, implicit by the SNCF because I presented my results to the SNCF, and they never told me this is unrealistic. Change your model. So this is my confirmation. But this question, I think, should be addressed in the perspective I mentioned on demonstrator, because on demonstrator, then we may see operational constraints like protection schemes, as you mentioned, that should bring more costs. And that's why also I didn't put AC costs in the base case, because I feel like it wouldn't be fair for AC, because it would like be, if I embed AC cost in the base case, I say, okay, you save AC cost and you have technical RMVDC cost, but I don't consider them. It's not quite honest. So I prefer to be on the same basis and leave maybe RMVDC cost for further investigation when with demonstrator, for instance.
Okay. I have. Now it's a very quick question and very precise. I was just, if you can just explain again about your sensitivity. So you made a sensitivity analysis. What it was really complete and it was really great to have this analysis. So can you just comment a little bit? I was just surprised. So in your base case, it's a 2 hours battery. And then you say, okay, I will study the sensitivity on this. And you study 1 hour and 4. And like, it seems like as if 2 hours seems to be the kind of optimum, let's say. I was expecting that, I don't know, maybe 4 hour would be better. So can you just explain and so why this 2 hours seems to be the optimal, or maybe it's 3. So why can we observe such results? It's not so obvious for me.
Yeah, totally. And it was a surprise for me as well when I looked into the data. But this has an explanation. So the buzzword is threshold effect, which means that at some point, when you decrease the size of the battery, you can't deliver all the energy produced by the HPP because you don't have enough flexibility. And then the HPP comes from, okay, it's a bit similar from the AC network because I will manage to supply all the trains, to, oh, I don't have enough flexibility. So I'm stuck. So when you decrease the size of the battery, you can have a threshold effect where it becomes irrelevant from start. So threshold effects are non-linear, so that's why we don't see the linear, indeed, optimum of the hour of the battery. And I would say for long time battery, it's not better, because at some point you have many flexibility and you have too much flexibility. And if you are connected to the trains, there's no point, because you can't, in the base case, you can't sell to the AC network. You are just limited to the consumption of the trains. So there's no interest in having large batteries, whereas in the AC network, if you have a large battery, then you can do arbitrage. And so that's why there is a threshold effect, and that's why. But in some cases, you can see that 4 hour is a good way, like this one and this one. And this is why in these cases there is a room for 4 hour batteries, because the train consumption is large enough. So, but it's not the case for here, where the train consumption is not large enough to bring the large batteries, and that's why it's not the best option.
Okay. And last quick question: why you did not model the reactive power support in this? Because it's something that is quite used now in both transmission and distribution system. So why you did not model this reactive power support as a service? Because I think you modeled the curtailment, but why not reactive support?
Okay. I don't know if my answer will be quick. I'll try.
Okay.
Because reactive power is indeed a huge topic. So basically, in all the thesis, when I connect DC resource, I decide what does the DC resource first. So here we have HPP for energy plus arbitrage and not reactive power. And I don't optimize the operation of the way the stakeholder is considering its battery. So I decided to compare arbitrage only battery. And you're right to say that operators that would consider reactive power support won't do that. But I can say that if you have reactive power support, if you want to connect to RMVDC, you need that RMVDC substation bring reactive power support, or at least I think it's not feasible to drive the reactive power support from the HPP up to the substation. It's like a different matter. So for me, reactive power support, I think from the RMVDC connection perspective, it should be investigated on the transmission substation. And but indeed, for me, if a stakeholder doing reactive power support with a battery tells me, should I connect to the RMVDC, I will definitely tell him, okay, if this is your mainstream of revenue, don't do that, because you can't, at this moment, you can't couple reactive power support. Thank you.
Okay.
So thank you very much, Marie-Cécile, for your questions. I have to interrupt you since we have a lot of other jury members and even a lot of questions. Thank you very much for your very interesting.
Okay.
So now I invite Professor Kutululis for asking his questions.
Thank you very much, and thank you, Laurent, for the presentation and the invitation, not from you, but from your supervisors to join the jury. I think for me it was also very informative to read the thesis, especially since I'm based in a country where railway is not electrified, so I really know even less about railway. But it was a very nice opportunity for me to get educated, I would say, on these topics. And I also liked very much the fact that you managed to convey a very, very, very large amount of information in a and do that still in a readable way and in a reasonably lengthy thesis. So I think that's also very, very appreciated. I think, of course, a lot of things need a bit of digestion to understand better and go into the details. But as you said, you already discussed a lot about the optimization part with Marie-Cécile, and there are other members of the jury which are much more experts in this part than myself. So maybe my questioning, it's a bit more general, at least in the direction of some of the assumptions. And I should also say that I like very much the fact that you actually pose very critical questions towards the choice of DC or not. I think it's very common that when a student gets a topic, okay, I'm going to look at the potential advantages of MVDC or any other technology, then we tend to favor that technology, even subconsciously, if you want. I think it's very good that you really put this to test. I actually have a very, very general discussion about these different voltage levels. You talk a lot about standardization and how much that will can have an impact on the results, and I fully agree with that. But I'm a bit curious about the LV versus MV versus HV in the DC world, because I think it's at least in my understanding that it's even more unclear than in the AC world. And I know that I mean a lot of your work is done under the assumptions of the French DSO. And yes, I was getting to this slide. Is the 50 kV? I assume it's a regulatory definition about the voltage level. What do you think about that? Is that helping us or not in our analysis or in our discussion about how our power system should evolve in the future?
What do I think of the 50 kilovolt AC
of all this regulation about a medium voltage and the requirement that you have to stop at 50 kV and you cannot go higher, for example, in some of your cases. The same with the AC. I think you do discuss about the AC limitation of the 63 kilovolts and how this impacts the results. But what about the DC part? And how useful are these limitations, you think?
Okay, it's almost a political question of unbundling and stuff like that, because you can see on this slide that indeed in France it's regulation, and for some reason I don't think I will comment on that. There is one monopoly from one side and several stakeholders on the other ones. I would say first consideration on AC, maybe it brings threshold effects. From an economist perspective, it's not very efficient, because you bring some kind of opportunity things with these gaps, with people doing like being in the corner of the threshold. So, well, that's my short comment on that. But I won't say that RT should open concurrency, because this is my future employer. So don't work my work. Okay. No, on MVDC, maybe your question is like, what should be the limit? What would be the limit on equivalent limit on AC and MVDC? On my perspective, for the moment, MVDC is rather, as I said, a non-standard solution. And I think it has to be digged. You know, MVDC is like a fact. It's an odd thing, okay? Many applications, many use cases. Should it go to TSO, to DSO? Well, I would say, okay, it doesn't matter. If TSO has a use for it, go for it. If DSO has a use for it, goes for it as well. So drawing a line is putting a constraint in an optimization problem, and you know all well that this increases the objective function. So I wouldn't draw a line, and I would consider MVDC as a fact for the moment and a solution for all stakeholders. No, for the standard of AC, I want to. This allows me to introduce you more in detail the results of the AC thing, and maybe also the limitation from an economic perspective, because standardization is also a thing. Okay, so this slide is quite important, I think, but I won't present that in the main presentation because it's a bit lengthy. So here is the base case result. You have green and red, you have AC and MVDC, but no, assume you can present 20 kilovolt, 33 kilovolt, or 60 kilovolt in AC. So now you compete at the same level to MVDC. And now you can see, so it's mostly red, but okay, the values are not that different. You can see the difference between MVDC and MVAC is low. So putting thresholds, putting standards from a perfect economical world, it doesn't help. And when you explore the possibilities, then you bring new technologies, and it's not the most optimist option. And when you see that, you could say, okay, so RT has to do 20 kilovolt as well. Sorry to say that, because it's a good option for this kind of use case. And finally, but you have to take into account standardization, which is a big. It has the advantage to do standardization. It decreases the cost. It makes mass production, etc. And I describe it in my perspective. Standardization is not a matter I tackle in my thesis. And I think to really complete the analysis I made and the analysis I made is the perfect economical world. But to complete this analysis, we would have to address standardization cost to finally describe if standards are viable for MVDC. So, broad answer. I hope this.
Yes, but isn't that, if I now understand a bit better, because it was a bit counterintuitive, as you said, standardization decreases costs because everybody knows how to design their products and everything is defined. But what you really mean here is not standardization as such, but it's more granularity of voltage levels. So you have access to more voltage levels than this, quite arbitrary. I agree with you, definition of where RTE's responsibility or jurisdiction starts and stops. So maybe voltage granularity is a better than standardization, because I think standardization sounds a bit counterintuitive the way you present it.
Okay, just to comment on that, it reminds me an ADEME report. So ADEME is a French energy agency, French agency for energy transition, and I thank ADEME to transmit me this report. ADEME is studying 33 kilovolt is France, AC, because 33 kilovolts AC is indeed standard, but it's not standard in France. So I agree that my use of standardization may be a bit confusing, because I mix up standardization of new technologies and standards in countries using other technologies. But in France, ADEME considered using 33 kilovolts with NADs. And the conclusion is a bit like, okay, maybe you can use this technology and it's mass produced in other countries, but still we have standardization costs, because at the moment, if NADs, I won't speak for NADs, but what I understand is if they want to apply 33 kilovolt AC, they will have standard costs. It's new technology, new management, new formations, new storage, new etc. etc. So for me, standardization embeds both the mass production of new devices and the application of one device in one country with some companies which are not used to the technology.
Okay, fair enough. I think this might have to do something with the cost learning curve and the cost decrease. I think you used the example of the PV, which is impressive, but might not be the best comparison here, because they are quite different technologies, and maybe the learning curve cannot really be as steep as it was for PV. I mean, wind, that was not the case for wind as well. But I think, I mean, my point was there that it is a bit of a chicken and egg, because a big part of a learning curve and cost reduction is industrialization. Standardization is one thing, yes, but also industrialization. So all your discussion about the cost of the converters, which is very correct. It's okay, I'm not using them because they are still rather expensive, but there's really not a chance for them, for their cost to decrease when they are not used, you know. So how do we deal with this chicken and egg kind of problem? In my, at least in my opinion, that issue, because you know, also comparing to PV, we will never have. Never, it's a strong word, but I think it's a very low probability that we will have such a large demand in terms of units or megawatts or, you know, gigawatts, terawatts, whatever you want the unit of converters compared to PV plants, to PV panels. So how do you think we deal with that? And I know it's very general, and I was planning to give that at the end to question, but we discussed the standardization, so maybe it's a good point to discuss that now.
Yeah,
how
perfect.
can we break this cycle?
Yeah, the keyword is potential and prospective studies. So I had a former life in a certain consulting company, which my RT colleagues are fed up with because I talk too much about it. But I did prospective studies before my thesis, and prospective studies are here for that. They draw the potential for a technology. So of course there are, as you said, chicken and egg, because in the prospective study, you take optimistic hypothesis, which validates the technology. So you have to increase. But I think, like for the energy transition, I would say that PV cost decreased because there was decarbonation, and many people said we have to install PV. I mean, it's to decrease the carbon production. So people were telling other people to install PV. This paved the way for prospective studies triggering the installation of PV, and motivated public support, which led to the PV story with the decrease of cost. For me, MVDC is a bit the same, in the sense of we have to address the potential, and it's what thing I did in my thesis, even if indeed I don't find 100 gigawatt of MVDC solution for railways. But we have to do prospective studies to see the potential of the technology, and then we can be confident, or at least convince decision makers to support the technology at first. And when the support comes, it can be good. And that's why also the debate is on electrolysis. I think Robin has a lot of discussed to that. Electrolysis, is it interesting? We need prospective studies.
I agree. Now you say electrolysis. Actually, before that, since you have the table on the screen, I spend a lot of my time, or a considerable part of my time, in the HVDC world, where we say that, as you said, distance is one of the main drivers, if not the main driver for DC versus AC, but also the high power. Here I see it's the other way around. You say that high power favors AC versus DC. Is that, can you elaborate a bit on that? Why is this the case? At least to me, it sounds a bit counterintuitive.
Okay, let me show. Okay, this this graph. So as you mentioned, this is a classic cost break-even distance graph for HVDC. So it comes from an HVDC paper. Okay, I would say in mathematical term, rating is ordinate to origin, I think in English. So it's, if you increase the rating, you make an homothétie of French term of these two lines, and you increase the start DC farther from AC. So the time to catch up with AC is more important. So basically, it's because of converter cost difference. So the cost to the origin is mostly converter cost, and when converter costs are important, with the rating, I assumed in my thesis they are proportional with the rating. Then yeah, it becomes more expensive. So that's why. Does that answer the question?
So your answer is that if you would go your table before more than 40 kilometers, at some point DC will appear also for the high rating, or I misunderstood your answer? I mean, I agree that there will be higher costs, and the initial difference between DC and AC will increase, although the AC station cost will also increase with the rating.
Okay. Sorry. Yeah. Look at my table. So we have gray areas here because, as I said, there are regulation thresholds in France, so I didn't explore like 100 megawatt for 40 megawatt kilometer, because it shouldn't be connected to 63 kilovolt AC there. But you can see it is decreasing. So indeed, at some point, if we continue the distance there and there and there, at some point, DC will become interesting. So the trend you are mentioning, I think you can see it in this slide.
Okay, I think fair enough. I had a question again from you showed the table before in the discussion with Marie-Cécile about the HPP part, and I know it's slide 50 something, but you had the last line was about wind. So your number of cases were decreasing or wiped out completely if you are considering wind. Yeah, this one. So
yep.
The last two, I mean, for the wind profile, I assume it's only wind, and you said that during the night there is no consumption, so wind is out. But also for the second one, wind profile and bidirectional, the power station for the 9, the 9 kilowatts L9, the last two columns, it's
yep.
wiping out all your choices. Why is that?
Yeah. So you're right to say that it's because of the night. So if you have a unidirectional substation, you are at night, no trains, wind power, but you have to curtail it. So that's why in the base case, I mean, in wind profile sensitivity analysis, there's no interest. Apart from, oddly, some sites are more interesting, but it's really few. On this side, it's because of voltage catenary constraints. So I think I detailed that in the sensitivity analysis. When you model our MVDC network, you can't inject full power all the time because you have voltage catenary constraints. And when you inject on the catenary, you increase the voltage of the catenary. So for wind, it appears, I think for solar, you can manage because the peak is only at one moment of the day. So even if you have this kind of effect in solar, the peak load is managed by the battery, for instance, and it's okay. But for wind, as you have very erratic production with a lot of peaks, then for large-scale power, here, because of the catenary constraint, it becomes irrelevant.
Okay, I think that's fine. It makes sense. I mean, I liked very much what you said, that the choices and the hypotheses we are making are very important, especially in this cost-benefit analysis or talking about the future. I was wondering, as a small thing, and then I'll move very fast to my last part, which I really want to discuss with you. You chose 10 kilometers as the distance from the railway for your HPPs. Do you think if that was 15 kilometers would have made a change fundamentally your results in terms of where AC is more, where DC makes sense or not?
Let me show the slide. Okay, it's this one. Indeed, you're right. So this is the threshold thing in light blue. I filtered on 10 kilometer. Okay, no, I don't think it will change because it's in the manuscript and the paper. I list like all the sites mentioning the distances between distances of sites to RMVDC and AC. It's true, you're totally right. I should have made the link indeed in my manuscript. But when we look into this graph, and let's say we could plot a heat map displaying the number of sites depending on both distances, and the number of sites which is far away. So remember, to connect to HPP network, you need to be far away from the AC network and close to the RMVDC network. This is quite intuitive. But if you are far away from the RMVDC network, there's no way you'll be far away from an AC network. There will be an AC network nearby, at least in France, where the AC networks are very well spread. So no, I don't think it would change. But you're right to mention I could have linked this 10 kilometer limitation with the heat map I did on the distances.
Good. And then before Jan will stop me, I really want to discuss a bit about the last part with the AC counterfactual. I agree entirely with you that, as I said, we tend to favor one solution over other by not including all the options. And I enjoyed you using the fact device that can do power flow. And in your 118 bus analysis, I think that was very clear that having the possibility to have a power flow controller on the AC network may change your results. But RTE has also a big responsibility towards system stability. I think Marie-Cécile talked a bit about the reactive power, but seen as a revenue stream, which I agree is relatively small now and maybe will be in the future. But your counterfactual is very good for flow control. But if you keep in mind the recent Iberian event, do you think that including reactive power support, not as an economic but as a technical constraint, would change the results?
You mean
What
especially
stability I'm referring to? Sorry.
Yeah. Stability. Okay, but you put your foot in a big door, which is ancillary services, so including stability and reactive power support, voltage support. I mean, so yeah. Okay, would it change it on this chapter? I don't think so. Okay, I don't think so because in my analysis, it's mostly driven by operational cost and investment costs. But I would say that we could provide, so whether we do really complex modeling with ACOPF for reactive power or even maybe NTP for stability, but that's another matter. But what we could do to simplify here is to embed, it's a bit the same approximation I did in chapter 2, is to embed in the converter cost the benefits that it could bring to the grid in terms of reactive power provision, like saying it's similar to a 30% STATCOM, something like that, and also an equivalent stability.
Sorry for interrupting you. I agree with that, but stability, the stability of the system, it's a bit like reliability. You have redundancy before, because what happens if you have a partial blackout? That part of the cost is or the benefit cannot be included when you just operate at the cost of the converter. No, I mean there is a big benefit part to maintain your system operating.
Yeah, but that's my point to say. Okay, but what is the value of making the system operating? I think we have an economic approximation, which is the equivalent device. To say the value is okay. If I want to make, if I want redundancy, if I want other devices, I install another device which ensure me to make this black start capability or stability. And this is the economic value you have from your converter. So that's what I do as a rough approximation. But also I didn't do that because it's also a very local question, I think, and it's hard to be general on these matters. So I think it leaves a field for really interesting question and to explore in specific use case where you know the grid is weak and you need application to sustain the grid stability. For instance, I totally acknowledge that MVDC may be an option. But I think it should lead to specific modeling, and yeah, it leaves the floor for research. But I think it's quite specific to local things, and yeah, not addressed in my.
I wish I was there so we can continue this discussion after the questioning. So I guess I have to stop now. I think I heard Jan, no?
I'm afraid, yes.
Okay.
Okay, thank you very much.
I hope somebody will ask you about what is your recommendation to RTE in general related to MVDC. I'm not going to ask that now, but I hope somebody else will ask at some point. Thank you very much.
Yeah, okay, thank you very much. That's a good point, maybe for the next interview. So maybe now I can invite Professor Brizet for asking further questions.
Okay, so I take the opportunity to thank in Paris PSL for inviting me to sit on this examination panel, which cover an interesting topics closely related to the work I'm actually involved as part of the Raccordé project you're still working. So I agree with the reviewer's assessment of the quality of your manuscript, okay, and which was evident during the oral presentation that follows the same structures than your report. I greatly appreciate the structure of your work and the detailed description of the models and the method you developed. What I really appreciate also is that the hypotheses are clearly stated at the beginning, and the results are thoroughly analyzed with due consideration to the assumptions, the modeling choice you made. Okay, so I would like therefore to congratulate you for your PhD work. There have been a lot of questions from the reviewers, but I still have a few that wasn't asked before. Okay, my first question is about the choice you made for modeling the complete year. In fact, you do not have 1 hour for each hour of the year. You choose a set of representative hours. So my question is, why don't you use a full year? So is it due to lack of data? Is it due to want to have the solving faster? Okay, so that's one part of my question. And the second part of this question is about the storage, okay? Because the energy in the storage is a state variable, so it's continuous. So how do you manage it if you do not have a continuous time during the year?
Okay, thank you very much for your comment. So indeed, I use 61 representative days. So I represent 1/6 of the year for chapter 2 and 3. Okay, what I did represent the full year for the base case at one point in my work. I mean, it's not in the manuscript, and I selected the 61 days so that the results would be the same as the year, and it divided the computation time by 6, basically. So it's a very practical way, and working more on that, I think, would need to do some kind of time step selection and day selection with more informative model than what I did, because I only assessed the full year. So there was a check, but I agree that it could be improved to consider more statistical representative days. Indeed. So in example, in the thesis of Heitor, I think, which I'm mentioning, there is a really good representation of the situations for its 50 hours. So yeah, okay. Now for the second part on storage constraint, what I do is I assume the storage level is back to 0 each midnight, which is, I explained that from a stakeholder's perspective. I think if SNCF and a HPP operator manage to contract to connect between each other, I think there will be kind of constraint on what can do the battery or not, depending on the day. So as the battery operator is not a perfect forecast, I don't think it will optimize like day to day. I mean, it's not sure. So I think this hypothesis is reasonable from a stakeholder's perspective. They can decide to operate the battery this way. No, what would it change if I would model the full year and look into the results? I don't think it will change a lot of things because the prices are quite continuous. So even if you don't fill down your battery at midnight, you will fill down it eventually at one other step. And I don't think the spread between the prices will be very different. So we will need a sensitivity analysis to prove that. But my intuition is that it wouldn't really change the conclusions of the work because the prices in France are rather, I would say, regular. And finally, okay, this. Oh yeah, okay. And also, it's a trick of modeling to state the variable at 0 at one point because it allows you to decompose the days so that you can optimize each day independently. But in the end, it's not what I did. I just brought the problem in total in the model with this constraint. But it could be also a thing if we would like to parallelize the model and test more hours or days. Days are more relevant for solar. We would need this hypothesis, I think.
Okay, I have also a question about hybrid power plants. When you connect them to the Railway MVDC, is only unidirectional railway substation. You consider different. You consider 3 different this hybrid power, okay? But for each power, the peak power of the PV panels, the power of the converter are directly linked to the power of the hybrid power plant. Okay, that's what you choose. And okay, you choose you take ratio from the literature. Okay. Okay, so my question is, could have these parameters, such as the battery capacity, such as the PV peak power, could this parameter have been decision variable in your optimization? And one part of my question is that the train traction power consumption is quite specific, and maybe there's optimal value battery capacity depending on the use, the typical railway use case.
Okay, yes, so it could be. It could be a decision variable. It's what I do in chapter 2. In chapter 2, the converter ratings are optimized. But when you want, so my philosophy in chapter 3 is to say, okay, you have a stakeholder, he has an HPP, he wants to connect it somewhere, but he made this and he wants to do arbitrage plus production. But he won't change the decision making of the PV rating, etc., depending on where it connected, and it's related somehow to the potential. I mean, if you have a field of 12 megawatt, you want to maximize the output, I think. So it could be a decision variable, but let's say it's not the philosophy of chapter 3. I think I could embed it, but this would bring questions on why would the stakeholder do only arbitrage if he connects to the AC network. You want to optimize his installation, its gain. You would have to optimize also just the NPV of the PV project. And then it brings many questions of design of the HPP. So indeed, I leave this question behind me on chapter 3 and take as an assumption, as you very correctly mentioned. No, for the optimal size of the battery, yes, I think your question relates to Marie-Cécile remark on counterintuitive results for batteries. Where is it? It's there. So do you take no battery, 1 hour battery, 4 hour battery? So obviously no battery is a no-go. But yeah, okay, 4 hour battery may be better in some cases for HPP. So again, it's this question of who decides the sizing of the HPP. And I think in the future, if SNCF wants to install this kind of installation, they will definitely optimize the battery. It's not a trivial matter. But for my study, which is studying the potential of HPPs, connection, having this as a discrete parameter allowed me to explore a wide range of cases without going into this discussion of what is the best option for PV hybrid power plants literature, which is very abundant, by the way.
Okay, so my last question is also about the hybrid power plants connected to the railway DC grid. So there are some problems for traction, okay, because you have a catenary voltage, and where there are big traction power, the voltage of the catenary drops. Okay, and if the voltage drops, then the power of the train must be reduced, and the speed of the train might be reduced also. Okay, so that's one point. And the second point is about, okay, if you take into account the point of view of the SNCF, the railway operator, so they pay for electricity, and so they have contracted power. Okay? And if they have power consumption higher than this, so they have penalty, mention the pure tariff. So it could be interesting to use battery for, so battery can bring additional services such as reducing catenary voltage drop, and also maybe reducing the contracted power, the railway operator. So could these services be included in the optimization, and what you think how it could be done?
Okay, yeah, thank you for this question, because it raises a point of the literature I didn't mention, which is train modeling and RMVDC modeling. So just to mention, my RMVDC modeling comes from the thesis of Andrea Verdicchio with the DC current. And yeah, and indeed there are literature on more complex system with, as you mentioned, speed of train, which is different depending on the optimization variables, etc. And in my assumption, my model considers that the trains go straight and without train station. So I think if I would bring train demand into a decision variable, it would be. I think the problem wouldn't be such the train demand, but the position of the train, because I model the position of the train and I assume it's fixed. But if you know the position of the train changes into the optimization problem, it may stay linear. Wait.
Sorry, but my question was more about the catenary voltage.
Okay, sorry, I'm losing myself in detail. Okay, catenary voltage. Penalties for going too far. Yeah, we could not. So for the penalties of power, we could model it into the electricity price, I think. Like you have the TURP, you have the production price, but if you are consuming electricity from the RMVDC network, you can add up an additional layer in the cost of electricity as the penalties. And you would apply it only on a part of the substation load. Like if the load of the substation is above one part, then there is an additional cost in the optimization function. And I think with a binary variable, you could manage to do that. You know, the binary would be: are you above the train substation rating or contract, and with the additional cost. And about the additional services of the battery on voltage drop, I think it's an hard constraint. I think I already model that somehow because I do model the voltage constraint of the catenary. And so in my numerical use case, the lower bound of the catenary voltage is never reached because my trend consumption in the hypothesis I made is too low, so I don't have this threshold effect. But if I add this threshold effect, I think I would see in the optimization the fact that the battery is drawing power to avoid and maybe to optimize the train. But the fact is that as I take a constant train speed, if I have this threshold effect from the start, it means that the hypothesis I made on the train are not correct, because it means that the train network can't work with the train's speed I took. I mean, because train speed is an entrance of the problem. So if I see that the threshold is broken, then it means the train speed is not correct. So it would need to go coupled, I think, with a train position modeling to be interesting, this question, and it brings quite a lot of work and good research for.
But I think no one wants the train.
Ah, yeah.
We also want I invite.
Thank you very much, Chairman, and thank you for being part of the jury. Laurent, I really enjoyed reading your thesis out of actually two reasons. One of them goes a while back, personally, because I did my PhD also in trying to understand when would you invest into AC and when into DC, building also large-scale mixed integer linear programs, but then it was more on offshore grids and high voltage networks. And actually, the second reason is at the moment, we are also involved in a project with some German distribution system operators, basically sub-transmission, where we are again looking at the benefits that could be brought by medium voltage DC. So I think this is going to be a very nice reference for it. So it was a very interesting read. But, you know, I have been asked to challenge you. So that's now I'm going to the role that I'm going to assume. My first question is, especially in chapter 2, you have done quite an, I would say, detailed modeling in looking at the cost of, you know, DC circuit breakers, transformers, and so on and so forth. So you actually built, I would say, a rather complex model. But then this is a lot of detail that you're introducing. But what does that level of detail bring you when you compare it to the uncertainty that you have with the costs? Because in your very introduction, you presented basically this these cost data, I think, from Rick de Donker's group, where you said, okay, the cost of DC has increased quite a bit. Same happened for AC as well. So what does basically the more accurate representation of all the components bring you with respect to the inaccuracy of the cost data that you have?
Okay, so I think the question is related to the fact that we are working on a prospective technology, right? Yeah. Okay, so I have from RTE, I had some contact with industrials, and of course I can't disclose the data I have. But the hypotheses I made are related to this industrial discussion, so it's not industrial data. But I think with all the discussion with stakeholders, with RT, with the literature, which can be really optimistic, I think I drew a fair line of what can be the maximum, the best cost AC/DC or DC/DC conversion can provide, and this is what I did in my sensitivity analysis on conversion cost. And again, I think sensitivity analysis is really needed, and I would relate that to DC breaker studies from INSOE, where in the offshore development they have two scenarios just for DC breakers. Is it a thing or not? So I'm also quite confident. If I have to quote one work, it would be also, again, the work of Heitor Farazdi-Barros, who did a really good work on listing the cost of converters in prospective studies. And in his optimistic use case of DC-DC conversion, either those use similar costs as what I did. So I'm aligned both with the literature, with the industrials, and I'm doing sensitivity analysis with present costs and prospective costs. So that's why I'm fairly confident, but in the end, it's a crystal globe, you know, prospective studies. So I can say for sure it will happen, but from far as I know, I feel confident in this hypothesis.
Okay, I might come back to that, but could you navigate to your slide 34? Because I think the other questions I've written down and
34.
34, yeah, I think can be visualized rather well with that. Yeah, perfect, this one. So my first question is, especially when I look at where you're allowing all the three candidates, that when you're building the DC link, it is in parallel to the series compensation, right? On the figure on the very right.
Yeah.
Yeah. Why do you think is that the case? I mean, I am a bit surprised with that because I would have expected either you have two AC lines that you have at SSSCs, or you might have two DC lines, but having one at SSC in parallel with the DC line was a bit of a strange sight for me.
Okay. Yeah, quite. This is linked to the costs, to the assumption cost of DC line. So it's small there, sorry for that, but this is a plus minus 20 kilovolt DC. And I assume in my thesis that these lines are cheaper than 63 kilovolt AC. So this line is due to capacity needs. It's not linked to flexibility or controllability of the flows. It's just it seems to be more optimal to have capacities addition between these nodes. So as the DC option there is the cheapest one, it's the one chosen. So that's why you have this parallel results.
Okay, so the DC line is for the capacity, and then the SSSC is a little bit more for the controllability plus capacity.
Yeah.
Okay.
Controllability is always on DC, so it's I didn't dig into which is controlling what, but yeah.
Okay. But then I'm going to come back to the costs again here, because if you actually compare now the costs between, let's say, your second option, AC and DC candidates, where you go to a higher voltage level for the DC, they only differ by about like 2%. And if I did not misread your thesis, for the SSSCs, the cost does not depend on the voltage level.
Sorry, could you repeat the cost?
For the SSSCs, you used always the same cost, so they do not necessarily depend on the voltage level of the lines.
Yes, definitely.
This line is clearly between two transformers, and others are between other voltage levels. So how would your results been affected with that?
From my understanding, SSSC cost depends on the reactive power it can inject in quadrature with the current into the line. So my sizing of SSSC depends on this reactive power injection maximum. So I don't make it voltage related. I just assume, okay, this SSSC can inject this reactive power, and I size it as a reactive power.
I mean, it's a serious element that you will have to insulate from the ground, right? Eventually.
It depends on installation costs. Yeah, you're right.
There is going to be some costs, I think.
You're right. Okay. My hypothesis, more precisely, is taken from Acer report, which bring ranges of costs for SSSCs, and I think I took the middle, the median, or close to the median. But I totally agree it would be an enhancement of this model and the hypothesis here. And it's true, it's a big debate, the cost in depending on the voltage. I did hypothesis for the lines, but for SSSC it may be current as well.
And, you know, being a professor in Belgium now, I have to come back to the foam on the beer, meaning the reactive power, because I think there was a little bit of a contradiction in the sense that when Cecile asked the question, you sort of answered it, I think, from the point of view of the single operator of a hybrid power plant, where at the point of common coupling, you will have some reactive power constraints that you can fulfill. That's nice. Then when you were talking about actually the chapter 3 work, said that the catenary voltage is going to be a limiting factor, and that might limit actually the amount of injections that you can have. But then looking at this picture, why should then here the voltage also not be a constraint? Because for many distribution system operators in Europe at the moment, the injections coming from all the wind farms or all the PV plants, they are causing sometimes more voltage problems and more curtailment than actually the thermal overload.
Definitely, and this may be also a question of distribution, but no, it's coming to transmission as well. Indeed. Okay, so indeed, I didn't model reactive power. I proposed, I mean, not in the manuscript, but right now, a rough approximation with the equivalent equipment, but it may be not enough to address local issues of voltage support. I think we would need to go to ACOPF. With this kind of model, it would be hard to...
Not necessarily, but okay, continue.
Yeah. So my point is to address, maybe it wasn't obvious, it was to address controllability of the flows for chapter 4 first, which is a big advantage of MVDC, as I mentioned in the literature with SOPs, etc. So what I say is SSSC is a very good counterfactual for controllability, and this is what I demonstrate there. And for going into voltage support and bring voltage decision, if we want to go deeper, ACOPF expansion, which is very computationally high burden, or with this rough approximation, but like the rough approximation for you may be a bit, I would be happy to have your opinion on that.
Yeah, I mean, generally, the world is not, let's say, only nonlinear or linear. There is a whole, I would say, plethora of power flow formulations you can choose. And basically what we do is we experiment a lot with different linear formulations where you can represent the reactive power and basically the voltage, obviously in an approximated way. You can use second order cone relaxations, STP relaxations, and so on. So I think there is a whole range of what you can try to implement. But you are right in the sense that if you want to solve a mixed integer problem, then moving away from anything that is linear is going to be a very big burden. And this sort of is my last question, actually, and this is where I really want you to hear a bit your own opinion, because sometimes I'm struggling with the same train of thought myself. So the main reason of using an approach that you show here is to deal, let's say, with the combinatorial complexity of where do I build all the lines and etc. Because for that I need some sort of an optimizer which only works in a linear way. However, and this is a discussion I think that you also had a little bit with Nikos already, is when you're moving to linear models, then sometimes you're not able to present a whole range of benefits that you could get from your equipment. And this is true for the SSSC, is true for the DC, is true for any technology that you want to consider. And also considering that very often the cost is not the true cost of the equipment, but actually the price that the manufacturer is going to charging you. I sometimes think it's more important to focus first on the benefits and then go and ask a manufacturer if the costs justify this, then I'm going to buy it or not. Which then means that you are actually not doing this combinatorial optimization, but actually try out some candidates. So I think this was your second slides or so, where you were showing a classical CBA, right? And what is your opinion about that? So do we always have to favor this, let's say, combinatorial approach to the CBA and trying out different candidates or combinations of candidates that might pop up? Should we always use the one or the other, or is there something in between? I would like to hear your thoughts about that.
Yeah, thank you. This is a question I asked myself all the thesis. You know, what is the level of approximation?
It's the one that I still keep asking myself. So.
Yeah. Okay. I think, as I mentioned in the introduction, CBA general, transmission expansion planning, or really complex integrating optimization such as this one, or it's not that complex because SOCP is more for more dedicated problems. So I think it may sound obvious, but the model you have to choose is associated with the question you are asking yourself. If you want to ask all the benefits, I personally think CBA is better at first. You first do a CBA, then you improve the level of detail of each component of your CBA. At some point, if you feel ready, you go for full optimization. But I think CBA is always a good start. Now, I would say, yes, there is a world in between, definitely, because CBA can embed optimization. And it's what I did in chapter 2. I have this rating optimization, which is inside the CBA. And it's a mild, between very simple CBA and really complex optimization. So first, ask the question. Don't try to deviate too much from the question, because then the model will change a lot. And go for CBA first, complexify, and maybe at some point, if you feel mature enough, go for full optimization. Because I think also when you study CBA, well, you are, apart if you are a large expert like yourself, CBA brings you new questions, brings you new, you can look into what is important or not, and it leads you, it paves the way for optimization afterwards.
Yeah, no, indeed. I think along the same line, so that's good. Thanks.
Very much.
This is Benoît Saunier. Yeah. This is Benoît Saunier from SNCF. Yeah, right. So, thank you. So some questions have already been asked, so maybe it will be more general comments followed up by quick questions for me, but yeah, let's go. And first of all, I would like to thank you for inviting me in your thesis defense and to congratulate you on both your reports and presentation, both of which I found were of extremely good quality. And I also like to express gratitude in the name of SNCF Réseau, and especially Mr. Caron and Mr. Retrouvé that could not be here today. And also for all the exchanges, during the recorded projects. I mean that you were a real link between what the work was undergone in RTE and the work undergone at SNCF. So a special thanks to that. Now, also, as the other member of the jury said, a special hat off to your synthesis work, because you had so many cases and you were able to make it understandable, both in your report and also in your presentation. Now I will mainly talk, obviously, about chapter 3 of your thesis. So your work is especially important for SNCF Réseau, meaning we are building, as you know, our strategy for the evolution of the DC network, whether we should switch it to the 25 kV AC or should we increase the voltage to 3 kV, 9 kV. So this work has been undertaken also in the Andrea Verdicchio thesis that you mentioned several times. And this choices is really important because it will have large financial consequences, both on rolling stocks side and infrastructure side. So your thesis gave us some insights, some arguments towards increasing toward higher level in DC. So this is especially important. And also you gave us one estimation of power that we could connect to this Railway MVDC. So also a particular appreciation of your sensibility analysis that gave us really a lot of indication on the location, on bidirectionality, battery sizing, this is all some conception points that we have discussed a lot into the Railway project. And your insight is really helpful for future projects for us. Some aspect of that will be explored in the future of the Railway project. I mean, bidirectionality, for instance, and also increasing the voltages. That's now we are working together with the RTE. I saw Xavier up here. Working in a project called GF4EU, maybe you know about that. So now for just a quick question, we talked about the advantages for HPPs connecting in the railway network. So we have talked about voltage level supports. We have talked also about reducing the power of the contract at the TPS. But also one of the main challenges that we have to face at SNCF is to optimize the braking energy of the train. So one question I didn't remember when I was reading your thesis is when you model your train, have you considered the braking energy?
Okay, I don't consider it because when we talk with Hervé Caron, yes, I thank you as well. The big support. We concluded that it was not worthy. No, it would be quite, I think, easy in the modeling to embed it because it would just be the train demand, which would be negative at some point. So you may want to manage that if you don't have bidirectional substations. But I think it's quite simple. You just can curtail it, for instance. And yeah, indeed, it would need additional hypothesis. So I built up the train demand with an own model, and I tested the train demand statistical profile with real data to ensure I was not doing bad train demand. But just putting negative train demand would bring this regenerative braking. But now it comes with also the question of Professor Brisset with, okay, but if the train breaks, it means the position changes and it's not a constant speed. So it needs another layer of train modeling with the braking. So it becomes more complex, but I think it's definitely doable if you know in advance the train schedules, position, energy.
Great, thank you. And also to follow up a question from Mr. Brisset, what is your lower bound on voltage at catenary level? Do you remember the value?
Yeah, it's 60 volts for the 9 kilovolt network, and I think it's like 63%, so it's 1 kilovolts for 1.5. I took that from Andrea Verdicchio thesis. He has a
okay,
table.
That's why I was wondering. So,
yeah.
Yeah, perfect. Oh, thank you. I think I had no further question.
Very much, Benoit. And now I give the floor to Professor Andrianis.
Thank you. So congratulations, Laurent, for the presentation. Thank you for these 3 years that I have to admit I learned a lot. And I need to say a few words, also thanking Laurent for inviting me when I was at DTU to co-supervise the thesis. I need to say a few words about Laurent. Laurent, he is not a power engineer by education. And he presented very, very technical details on the power engineering discipline, also on the railways. So this was quite difficult in my opinion, and also reveals like a strong background to be able to navigate. And I'm glad that you advanced in these 3 years and you actually managed to enjoy your PhD. I have 2 questions. So in your last chapter, you discussed connecting DC resources, and I know that your future job at RTE is going to be on scheduling outages, which is related to the network to network design problems. Do you see any connection on extending the work of chapter 4 with your new roles at RT?
Yeah, definitely. So I just put up this slide to remind that in chapter 4, we are indeed looking at the presence or the absence of some lines. And as you mentioned, outage is a bit the same question, because when you have an outage of a line, it's not there anymore, and the topology of the network changes as well. So indeed, my future work at RTE will be really linked to this chapter, and I thank you for asking the question. And I think the ultimate goal of outage has the same philosophy as this one, because you can, ideally, you can optimize the network, and the presence of the line or not is the same thing as installing a new line. And it brings up to new techniques which are developed by my colleagues, which are like considering a full network with a two-part optimization system, like using a Bender's technique, then the modeling of the network and compensation on both sides of the lines. Yeah, my intuition is that for outage planning, we need to dig into this kind of application. It will be computationally a big burden, but still the philosophy of coupling time steps, removing lines, adding lines, I think is the same for investment and outages, or planned outages, at least when you know the time. So there will be definitely big links, and that's why also I was really happy to develop on this chapter to be able to enhance my knowledge on that and start my new work at RT.
Thank you. I'm also happy to see that you are advancing in optimization, as it was not in your background. I have to admit that as well. And because Nikos was the first person I actually talked to when I called in your thesis about MVDC and discussing it, Olivier, who was very helpful in understanding the technical aspect mostly. So I cannot not ask his question. So what is your recommendation to RT on the MVDC?
Okay, two recommendations. First, do a demonstrator. Yeah, just you shouldn't go for the full technology at this point. You have to demonstrate its usefulness. So I think demonstrator, even if it's obviously not economically convenient at this stage, demonstrator brings you a lot of information, of data, of practical, etc. So it may be really interesting to demonstrate the technology itself. And the second recommendation would be continue prospective studies and look into the literature review, even if it's not you that are doing the work. Look at Professor Ergun project, European project. A lot of work is MVDC will live its life without me. I mean, a lot of people will work on MVDC. So follow the literature, follow the research, and keep aware, because as I mentioned, there is still ongoing work on AC versus DC.
The same holds for NADs?
The same for holds for NADs, and I aim to present them my results. So okay. I'm wondering what they will see say.
Great, congratulations again, and thank you.
Okay, thank you very much. Then I go to Dr. Despois for the question.
Okay, thank you very much, Laurent. Congratulations for your work first, sorry, and for the very nice presentation you gave us this morning. I fully support the very good, the positive comments that you received this morning from the academic side. I won't repeat them. I guess my role is mostly to give an industrial perspective on your work. As I mentioned during the introduction, we had this initial question about the viability of MVDC mainly for two reasons. RT is a bit specific in Europe because we operate at high voltage, but also sub-transmission network. So we are quite prone to dig into this medium voltage area. And second, coming from a more technical side of DC, I was quite aware of a lot of technical benefits from DC capabilities. And so we were a bunch of people really expecting MVDC to be the next big thing for RT. On the other hand, there was not so much literature about this, the economic viability of MVDC. So I'm really happy that you have investigated this, and I think this was really important for RTE because you have developed a very rigorous approach, and you, as I think it's Niklaus mentioned, that you kept a critical eye toward DC technology while it was your topic. So it was really rigorous and convincing as an approach. And I think it was very, very helpful for us to also to dampen some very optimistic conclusions from some part of the literature regarding the use of MVDC for transmission network operators. So thanks a lot for this. This brought to us some significant answers. I would like to stress also the fact that you really answered the industrial expectations from RTE. I heard also from SNCF, and you managed to do this research work while answering also an industrial project which is raccordé. And it was a very significant contribution that you made to raccordé for RTE. I think, as Panagiotis mentioned, you managed to cover a wide range of topics. You did DC technology, you did optimization, you dig into transmission networks and how they operate, how you connect clients, railway supply and networks, CBAs, etc. And you managed to investigate all of those topics with a very significant depth and to some extent, sometimes even much deeper than what I would expect from you. So it was really, really nice. Thank you for being so curious about those technical topics. It was a great pleasure to have you in the team during those 3 years, and so I sincerely appreciated to have you at RTE. And well, as you said, this is not the end of the story yet. So congrats once again, and I don't have any question for you. Thank you, Olivier.
So thank you, Olivier. And our next jury member is Dr. Clément. So the floor is yours for your questions.
Well, I will be really quick. I don't have any questions neither, as I followed your PhD. I just wanted to say that I really appreciated to have the opportunity to follow your work from the beginning. I've not been really involved in the last few months, but I was still able to appreciate your work and the consistency of your work and the quality. I also wanted to highlight the quality of your manuscript. Be clear, and there was a lot of things in your manuscripts. Also, well, I want on the relevance of the subject for RT as a thing, I guess. Of course, chapter 4 was the most interesting for the future at RT. Yes. Also, I think chapter 4 on the work you did with the SSC is really relevant, and also it highlights the fact that you were able to take a step ahead of your work and see that and you could question the limits and the strengths of your. So for that, I would say because it's not easy when you're studying one subject to. Congratulations.
Thank you, Hélène.
Okay, thank you very much, Hélène. Finally, I also have the honor as chairman to ask you some questions. So if you go back to slide 16. Yes. There you make a comparison between AC and DC, where AC or DC would be more favorable as a function of the transmission line, as a function of the length of the line. And you refer to second reference of the year 2015, but there was no voltage mentioned. So can you elaborate for me, very short way, what should be the difference between an AC grid versus a DC grid in a length, if it's a low voltage distribution, if it's distribution end user, if it's medium voltage distribution for industry and SME, or high voltage for transport? Should there be a distinguishment in distance or not, and why? What do you think with your research that you have done?
Yeah, I'm so taking back to standards, to AC standards. If you impose the AC standards, I think you'll have the same results, because if you are in distribution and you impose 20 kilovolt AC, and you allow yourself to navigate through different DC voltage levels, at one point, one DC voltage level will be cheaper because of insulation cost, etc. And so if the line cost is cheaper, it means that at some point with the distance, DC will win over AC. So so if I say it mathematically, the derivative from this line is really linked to the line cost in euro per kilometer. And if you compare solutions where in DC you have plenty of voltages, and including a low voltage solution with low line cost, and in AC you have just one line cost, which is quite important. As the derivative of this curve is not the same, at some point you will reach a point of intersection, but this point will change, obviously. And I would add a reserve on that, is that on low voltage side, I think we have technical constraints on the maximum distance of AC lines, which I didn't discuss in my thesis, because I think it's less the case for high voltage, even for underground cable, it may be a topic. So without the technical constraints, I think we would find the same results.
And another question with respect to your APEX and CAPEX analysis between AC and DC. What I didn't find back was the difference in cable losses if you work in AC or DC, since cable losses determine the OPEX of your analysis. So can you explain why you didn't explicitly mention that in your work?
I fear that maybe my manuscript wasn't clear, but I do make the differentiation. It's when we compute the losses, I do consider the number of conductors, and computing the losses in terms of losses per conductor, taking the AC formulation with the square root of 3 and the cos phi, the power factor, and the DC formulation. And I do separate the computation of losses between DC and AC in chapter 2 and 3, but maybe it's related to the remark from Marie-Cécile on OPEX, because fixed OPEX doesn't embed loss, and usually OPEX are with loss, so maybe the term was not correct. But if you look into the loss cost computation, you'll see the difference between both.
Okay, thank you very much.
Okay, so I have the last word. And so I would like to thank you first, Laurent, for the great work you've done. It was a pleasure working with you during this PhD. Also, I would like to thank RTE for inviting us following this work. It was very interesting. Also, at the beginning, a bit out of my scope of research. I had never worked with DC before, actually. So I discovered all that with you, and it was a tricky subject because you were asked to see the benefit of something that finally you could not find the benefit of, and it's really more difficult to find something that doesn't exist than to find something that exists. And but you found it, and you search in a very nice way in this very technical question. Also, you had 4 supervisors on the technical side. I was more pushing on the economic side. There was optimization that was important for others, and you managed to produce something, I think, that is embedding all of us in your work, and that's very nice. Also, I appreciate that in the complexity of this, you choose to go from cost-benefit analysis to more complex analysis that allowed you to see things that are not usually included in the optimization problem. And so it's a very nice piece of work on all of the sides, on the economic side, on the technical side, and also optimization part. So I'm impressed by and the weather also is impressed. So thanks a lot for that, Laurent, and it will be a pleasure continuing to work with you in the future.
Thank you, Laurent.
I think now we have time. We need to take some time to deliberate. And so we'll be back in. Oh yes, Christian. You have to ask if there's someone.
So first of all, I have to thank the distinguished jury for the question, but it's a public defense, and a public defense, the public may ask questions too. So I invite all of you in order to have some questions. So please, you can ask very difficult questions, but maybe also very easy questions, or maybe no questions. That it goes faster with the deliberation, but at least one small question from everyone may ask. Nobody? Okay, then I think I can conclude the public defense, and the jury will deliberate together the evaluation of Laurent. We will see each other within. Thank you very much.
Online, Ok. Ça marche. Oui, t'as raison. Okay, Laurent, Chiati, you can stay because for the deliberation we will switch there. Oui, c'est normal. Yeah, I wasn't expecting the. We should not ask questions.
Yeah, Mary-Christine can hear me, or Mary-Cecile can hear me. So, take the official note that we made together here. The PhD candidate, Laurent Cornaggia, gave a clear and comprehensive presentation about his research topic, introducing DC, starting from end users up transmission systems, and highlighted the research topic, namely the economic viability of medium voltage DC grids, including the challenges related to the utilization of medium voltage DC. Also, both research questions, techno-economic methods, and connection methods were clearly highlighted during the introduction. His presentation was engaged and clear, and also effectively completed to the manuscript. He also enthusiastically discussed the whether or not hypotheses if DC grids were feasible, and finally specific contributions as a part from the method itself were in-depth analyzed and explained, including the potential and sensitivity analysis for railway medium voltage DC ground connections, and made a comparison in operational costs between both AC, DC, and SSC. Laurent closed good motivation key takeaways. Yeah. His responses to the questions related to the statement and approaches he made in his thesis were clearly answered, and that extended beyond his immediate modeling framework, were perspective, reflecting both his maturity and in-depth analysis and his capabilities, including an extensive literature study. From the perspective that he doesn't have an electrical engineering degree, comparative studies between AC-DC networks were made even more challenging for him. In the light of this outstanding performance and the high quality of the manuscript, we are pleased to award Mr. Laurent Cornaggia the title of Doctor of Physics des procédés à l'école des mines PLS. Congratulations. So, and now the floor is yours.
Thank you very much, Mr. President. Thank you very much for all the jury for coming here. Very happy to exchange with you. I think this leaves very interesting research questions for the future work. Even if I won't work directly on MVDC, I'm really happy to discuss with you on these topics if you want to get in touch. Well, I would like to thank also my supervisors, and I have a few words for each of them. Yeah, so it's my turn to comment. So first of all, Robin, my director, thank you very much for this the opportunity you gave me, because it's Robin who built the topic with Olivier, and I was merely invited to the topic and go into it. And I think your perspective vision is really important. You really brought the political inside and applicability inside, and I think it's really important not to be always too technical and sometimes to reflect on what is useful or not. And you definitely ensured that we were looking at coherent things and useful things for the energy transition as well, which is a matter we both have in mind, I think. So thank you very much for your direction, and very appreciated. No, on the academic side, Panagiotis, so special thanks for you. There have been hard times between us, because I was a consultant, you know, I managed a bit of people, and now I'm managed by a guy who's he did the army in his youth, so it was, yeah, muscular, yeah. But in the end, I think we both reached a really good state of the work. Really good exchange. You learned me a lot in terms of reading. Your rigor is excellent. Honestly, you may be the most rigorous person I know in terms of redacting. So it's good when you read it. It's not good when you read me. But still, I think the work we did on the paper, which is, I'm really happy about it. Also, it is really good, and I'm looking forward to work with you, Panagiotis. Thank you very much. Now on the industrial side, Olivier, so you bring with this a bit maybe naive approach at first on MVDC, and you were really disappointed, like at the beginning of the thesis when I did Excel calculation and I said, hey, come on, the number doesn't add up. MVDC may not be the best option in any cases, but you passed this challenge and you helped me to investigate more use cases, more techniques, and in the end, I think we provided a fair comparison between AC and MVDC, and we did find topics where MVDC was useful, even also for RT. So it was a really good exchange, and I will work with you in the coming days. I'm in your team. You're not my manager, I know, but still I owe you some respect, right? So yeah, a pleasure to work with you, and many thanks for all the industrial intuitions you had. It was really precious. Hélène, thank you for following me during all the thesis. You were here at the first, then you left to far countries such as Lyon and Jonage. Maybe all the R&D of RT will go with you at some point. It's another topic. So yeah, thank you for your always constant presence and the proofreading you made. I think you ensured as well to have a good quality of writing of the papers, and to ensure that the industrial applications are here as well. Okay, so that's for the supervisors. No, I will be short, don't worry. I want to like all my colleagues. These 3 years were honestly really wonderful with you. Even maybe better than Artelis, I don't know, you'll compare. But yeah, I mean, the work at RT R&D is really, really appreciated. And I'm lucky because I think in my work experience, I not only experienced good environment of work. And I know from friends that it can be different sometimes. But RT R&D, I stay here also because of the people. And so this is because of you. So many thanks to all my colleagues. And I would like also to thank my friends who supported me with my stuff about MVDC, DC stuff, etc. And family. Special thanks to my dear Odile, who who also helped me when things went tough with Panagiotis, you know. And the word dragon was mentioned at some point, I think. And okay, your support was definitely appreciated, and really happy to share your life. Yeah, family, thank you for all, and special thing to the small Lucienne, who is 11 months and can't be here because she would cry during my presentations. It's a bit annoying. She'll learn. Okay, I want to make just a small statement of the fact of doing a thesis on late, because I have gray hairs, you saw that. I'm not the usual student, PhD student with all fresh, etc. I have a consultant or also engineering experience behind me. And yeah, I would advise definitely now to make a thesis at some point of the career. So, well, it depends if you want to go full academic or not, but it's really a great experience to work on your topic, to be able to have the time to dig. I mean, it's quite simple in the PhD, but it's true. You have the time to dig. You have not interference with politics or so, maybe a bit, but not too much. So I wouldn't definitely advise people to make PhDs at some point if they feel comfortable with it, of course. And for me, it was a great experience. I would like to conclude to dedicate this thesis to my father, who's here. Where are you, Christian? You're shy. Papa, tu peux lever la main. Ah, hello, Papa. He's very shy. He's very shy. So, Papa, you say you never encouraged me to be an engineer, but you talk engineering all the time at home. So maybe there's a bit contradiction in there, but yeah, really your support was wonderful during all my life, basically. So thank you for that. And also, I would like to end with a joke I make with my dad. Is the fact that you heard, some of you heard of it, is the fact that all my life I wanted to understand what my dad was doing. He's doing strange stuff. He's playing billiard with electrons and photons. I don't understand anything of what he's doing. All my life, I wanted to understand what he was doing, and that's why I did science as well. I still don't understand any of it because it's quantum physics. But no, I hope that you don't understand what I'm doing either. Okay, and so with this, I invite you to the small reception. So we will leave with the jury at 1:10, something like that, because we have to go to the restaurant afterwards. But really happy to welcome you, and thank you everyone for coming here or listening to me and live. Thank you. And thank you online. I think we can close the YouTube channel. Thank you, Marie-Cécile. Thank you also, Laurent, for the technical support. So,
thank you. Enjoy this moment, and sorry again for not being there.
No worries, I understand. Thank you, Marie-Cécile. Laurent, I leave the room. Oh, il est peut-être pas. Okay, I stop. Thank you online.